seeks to develop and implement effective course of action. Okay, so this is our mission in this department. Do you like it? It took us a lot of time to arrive at a conclusion like this, but I think it's a nice statement which tells us all about our educational purposes and not only educational purposes, but all of our purposes of our department nicely. The important words or concepts I have shown them, underlined them in red. So what do we do as industrial engineers? We try to create value in social technical systems. That's what we do as industrial engineers. Or rather, we try to educate engineers who are capable of doing this, which means you. And how do we do this? Is indicated in the second line of red underlined word. It says we depend on critical reason and systems thinking and strong quantitative analysis. Okay, so that's our mission statement. Now, let's leave it there, and again, before starting formally, let's look at some definitions, because we use a lot of terms, concepts, some of which are familiar to them, you know what they mean, but some of which are a little bit confusing, because the terminology and the terms that we use in systems thinking and in operational research in general are not exactly scientific terms, and they don't have one single definition, because they also occur in everyday language and people understand different things from these. So let's try to make things concrete and remove any possibility of misunderstanding by remembering these terms. The first term that we shall be using a lot is inquiry. Inquiry, it's also spelled with an E at the inquiry or inquiry, which are the same. It is any process that has the aim of augmenting knowledge, resolving doubt, or solving a problem. Augmenting means enlarging. So any process that enlarges our knowledge, that removes doubt, or solves a problem, such processes are in general called inquiry. Then we have the word research. We have used and heard about research a lot. What's the difference between inquiry and research? We define research as a kind of inquiry that can be defined as the search for knowledge, or as any systematic investigation with an open mind to establish new facts using a scientific method. So you can see that research is quite similar to inquiry, but the main difference is this method, scientific method. In research, we rely on scientific methods. So research is scientific inquiry, if you like. So inquiry is more general. Why do we make a distinction between inquiry and research? We will clear as we proceed in this course. Another term that we use a lot is the term method. Now, what is a method? Methods tell us how to use techniques in inquiry. So a method is something which tells us how to use a technique. I'm not going to define what a technique is, because then we shall need other definitions and there's no need to go into such detail. But as examples, from examples, you will understand what a method, an example, for example, an optimization method that uses differentiation techniques. You are familiar with these sort of methods in calculus and in optimization. So optimization is a method that uses a technique like, for example, differentiation. Or you could use other techniques that doesn't rely on differentiation only, but just as an example. Or another example could be a work study method using motion and time measurements. So motion and time measurements are techniques, measurement techniques, and the work study method tells us how to use those techniques in work study. This is, again, something familiar to you. So we now understand roughly what a method is. We have to now go on to a methodology. A methodology is the study of methods that are applied in inquiry. It tells us how to use various methods together. So methodology is different from method Because the subject matter of methodology are methods. Methodology is the study of methods. Finally, let's come to systems thinking. I mean, we're not going to define what systems thinking, but classify it among all these items. Systems thinking studies methodologies from a systemic point of view. It tells us how to apply them effectively in inquiry. So, if you go back to methods, we have methods. Then, in order to understand how methods are to be used in inquiry, you need methodologies. And in order to understand how methodologies can be used, we need systems thinking. So you can see that all these three are embedded within each other in a hierarchy. I would like to also make a distinction to make sure that you understand the difference between method and methodology as follows. You know, you have studied also the linear programming. It's an optimization method. And what method do we use in solving a linear programming problem? What's the name of the method that we use most often? It's the simplex method, isn't it? The simplex method. Another word that we can use, substitute for the simplex method, could be what? What could be called the simplex method? What's the other way of calling it? The simplex? Algorithm, right? The simplex algorithm, right? So an algorithm and the method are more or less look very similar, and more or less they are the same thing. I mean, formally they are not the same thing. It's an algorithm. A method is a broader concept, but for our purposes, we can think of a method as an algorithm. The distinctive feature of an algorithm or a method is that it's a step-by-step procedure. That once you start, you know how to proceed exactly. You know exactly how to proceed. You know exactly what the next step is after you've making one step. There's no doubt about the next step. The algorithm or the method tells you exactly what to do. That's a method. Okay? But let us assume that we have the simplex method to solve linear programming problems, and we are going to use this method in inquiry in general. For example, in a production problem situation. Okay? Then we need to know something more. We need to know how to use this simplex algorithm or the simplex method in our inquiry about the production problem. Here we need some guidance. Okay? The simplex method cannot tell us exactly what to do in this sort of inquiry. The answer to this uncertainty is given by the methodology. The methodology tells us how to use these methods. Okay? The difference between a method and a methodology is very important. In methods, all the steps are predefined, like an algorithm, and there's nothing else to decide. In a methodology, at every step you have to decide what you're going to do next. Inquiry and research in general are difficult, as you know. Science is not easy. Trying to understand the world is a very complicated problem. It's the central problem of all human beings. Trying to make sense of the world. This is the object of our life. And it takes effort, and you cannot use an algorithm to answer questions such as this. Okay? You need to decide at each step what the next step should be, yourself. So that's the distinction between the method and the method. Is this clear? Now, you can always stop and ask me questions. Okay, this is an important course. You can always stop and ask if you don't understand. I don't mind repeating. Okay. So, are there any questions about these definitions? I think it's pretty simple. Now, here is a graphic illustration which kind of maps the content of our curriculum in this department. Our curriculum is the list of courses, as you know, that we teach here, that we take in the department. And if you are successful, you get a degree. You get the Bachelor of Science degree in industrial engineering. And all these, our curriculum can be assumed to consist of two groups like this. There are the methods and there are systems thinking. Now, you can, I have written for methods theory, if you like. You can, liken this to theory. And in systems thinking, I have written the word application. Now, theory and application are not as straightforward as this, but it just helps us to understand. Now, we study in most of the courses you take in the department, you study methods. These are disciplinary methods that come under the title of disciplinary inquiry. A discipline is like a profession. Huh? Without going into formal details, we can call, for example, engineering, electrical engineering is a discipline. Chemical engineering is another engineering discipline. So is industrial engineering. Physics is a discipline of science. Okay? So we learn engineering, the disciplinary inquiry concerning engineering, but management also, we learn management in our department. We take courses on economics, etc. So that's disciplinary content or disciplinary inquiry. And also we study quantitative methods and mathematical modeling, such as optimization techniques, stochastic processes, modeling in these areas, statistics, etc. Okay? Of course, you could call statistics as another discipline, but it doesn't really matter. So we learn methods concerning disciplinary inquiry and quantitative methods and mathematical modeling. These are the backbones. Actually, quantitative methods and mathematical modeling takes the largest portion of our curriculum, as you know, and that's the backbone of our educational program, as well as the backbone of our profession, of your profession as industrial engineers. But then there's another box over there called systems thinking. And in this, of course, systems thinking, the content of systems thinking can be found in some of the courses we teach over here. But we think that it is not sufficiently present in all the other courses. So we have this present course on systems thinking, IE398. The right-hand side box consists mostly from our systems thinking course, and also other bits and pieces of knowledge and discussions included in here. So in systems thinking, what do we learn? That we learn, for example, hard systems thinking and hard operational research. In fact, I would have said here the methodology of hard operational research. And then we also learn soft system thinking methods, which include soft operational research. And we are going to see, for example, Checkland's soft system methodology. And there are many others like SODA, SAST, etc. These are acronyms. The SODA is Strategic Options Development Analysis. SAST is something like that, doesn't really matter. But there are many, many methods. So systems thinking, as the previous slide told us, is the study of methodologies, and these are roughly the methodologies we use in industrial engineering. When these two knowledge come together, we have industrial engineering practice. The practice of industrial engineering that we're going to be involved in after you graduate will not be complete without either of these two. You need both. Okay? So let's now make more comments about systems thinking, trying to understand what it is. Well, I'll give you a definition. I don't like definitions very much. I mean, in this course, if we try to make the course a formal methodology course, it will be difficult. And we shall be involved in detail. So I don't like definitions very much, but I'll give you a definition towards the end of the lecture. And then there are definitions in the book and in the readings that are assigned and that will be assigned. But first of all, it says this systems thinking provides the basis for industrial engineering practice as a background. It's a prerequisite for making sense of human activity. Again, the words underlined in red are the key words. So we have to make sense of human activity. It is a prerequisite also for structuring issues and for defining problems. Now, again, for the first time we have here two concepts which are similar to each other. One is the concept of a problem, with which you are familiar, I suppose. And the other is the concept of an issue. I don't think that we have a satisfactory Turkish word for issue. An issue is more general than a problem. The distinction between the two is that a problem has a structure. What do we mean by structure? Well, we'll talk about those later on, but you can at this moment understand that if something has structure, it is well defined. Okay? An issue is not a well-defined concept, or issues are not well-defined problems. Okay? An issue. So if you structure an issue, if you impart structure on an issue, if you give structure to the issue, it probably gives back you some problems. Problems are obtained from issues by structure. Sectionları birinci section'a topladık. Dolayısıyla bu 92 öğrenci arasında isminiz vardı diye ümit ediyorum. İsminiz olacak sanıyorum. Siteye girdiğinizde tabii siz böyle görmüyorsunuz galiba ama işte şöyle bir şey var, lecture 0 var, lecture 1 var, altında reading var. Yani reading bu demek ki bunun altına koyunca bu lecture'la ilgili oluyor. Our changing concept of the world adındaki makalesi oldu. Onları falan yükledim gördüğünüz gibi. Burada bir de additional resources diye bir bölüm açtım. Bununla ilgili kısa bilgiler bu doc file'in içinde var. Yani buradaki additional resource'lar mecburi olmayan resource'lar. Ama akıllı bir öğrenciyseniz onları da okursunuz. Faydalı oluyor yani size. Burada ECOF'un 4 tane kısa konuşması var kendisi üstünde. Onları dinlersiniz. Bunların ne olduğu, bir de burada Rosen'in bir makalesi var. Bunları mecbur tutmuyorum çünkü ağır olur diye ama kompleksiteyi anlatırken 4. lecture ediyorum. Bu makaleyi kolay. İçinizde okuma yazmaya meraklı olan öğrenciler çıkıyor bazen. Onları düşünerek. Yani dolayısıyla demek ki ben burada bugün acayip şeyler alıyorum, hala anlamadım. Without a good conception of systems, the link from quantitative analysis to management practice will not be complete. Okay, we need this methodological knowledge to make efficient use of the quantitative techniques and mathematical modeling skills and other disciplinary inquiry in our work. Designs will not work out as planned and attempts for improvement will fail. Okay? Attempts for improvement, as we shall see in our lectures further on, that the purpose of industrial engineering is to secure some sort of improvement in human activity systems, and that will not occur. So we have talked about disciplinary inquiry, disciplinary thinking, and also scientific research, as we mentioned. So we repeat those concepts under slight modifications as disciplinary thinking, which can also be called traditional scientific thinking. Okay? This is therefore part of systems thinking. System thinking contains and complements. Complements means makes it a whole. Makes it a whole. So it adds what is missing from disciplinary thinking, which is the traditional scientific thinking that we are familiar with. Okay? So that's the function of systems thinking. It's to complement scientific thinking. It is especially important in operational research and industrial engineering. And without a dedicated course such as our course, it would be missing. It would not be sufficient to talk about this in other courses. And the second paragraph tells us that trying to teach systems thinking by talking about it in various courses like OR1, OR2, etc. really doesn't help us very much. And it also weakens the learning of disciplinary content. You see, most of the courses that we offer to you are about mathematical quantitative techniques and mathematical modeling, and it's important to learn them properly. If you go into system thinking in those courses, the objective of those courses will be harmed. So this course tries to remove these deficiencies. Now let's talk about the first question, the answer to the first question. What is industrial engineering work about? What do IE people do? Well, IE seeks to improve organized human activity. As I had said just a few minutes ago, our profession tries to effect to produce some improvement. This improvement is in organized human activity. Organized human activity takes place in organizations. So an organization is a place where humans come together and are active for some purpose. And an organization can also be called a human activity system. So these are concepts that are used a lot in systems thinking, which are concepts familiar to all of us, but maybe the terminology is a little bit new. Human activity systems have the attribute, have the property of being social systems. There's always one or several technical systems embedded in all human activity systems. For this reason, human activity systems can also be called as socio-technical systems. So now you're getting familiarized with all these terms that we're using all of course. So what is the broadest concept? The broadest concept is a human activity, the concept of a human activity system or an organization. The work of industrial engineering is about organizations, always. Organizational issues and organizational problems are the subject matter of industrial engineering. The property of this human activity system is that it's a social system. embedded in this large social system, there may be one or more or several technical subsystems or technical systems. As you can see from this discussion, that systems are within each other. We could have called them, for example, the technical systems can be called subsystems of the social system, but there is no need, it's just another system. So systems usually come in hierarchies. There's a large system, there's a smaller one inside, there's a more small one inside, etc. So technical systems are embedded in social systems. And another way of calling a social system or a human activity system is to call it a socio-technical system, because it is both, it has both social aspects and issues and also technical issues. All engineering work has a social context. Context is the background embedded into which all the other things are. All engineering work actually has some social aspects, but non-industrial engineers, non-IE engineers, that's all the other more traditional engineering disciplines such as chemical engineering, mechanical engineering, etc. They can focus primarily on technical aspects of the social technical system. They can focus and spend their energies on studying the technical aspects. Industrial engineers have to focus on both the social and the technical aspects of human activity systems. This makes us a little bit different from other engineering disciplines. I'm sure all of you are aware of this. How different are we? How different are we from other engineering disciplines? Well, engineers are concerned with goal-seeking systems. A goal-seeking system. I'm not going to define these formally, as I said. It's just sufficient that you understand what we mean. A system has a goal. A goal-seeking system is a system which tries to achieve an objective. Engineers are always concerned with such goal-seeking systems, but mostly these systems, such systems, can be assumed closed. So now we introduce a new concept about systems, and you can understand from this that they come in two types: closed systems and open systems. Again, we're going to see what these mean in detail later on, but primarily engineers are concerned with systems. We're not saying closed systems, but we are saying which can be assumed. Can you give some examples for closed systems? Can anybody give me an example of a closed system? Just make an attempt. Just give me an example that you can think of. We didn't say what an open system is. I'm not sure we can say what a closed system is, but can you give an example of a closed system? Is this pointing towards a closed system? But to be closed, probably it should be capable of being isolated from its environment. The concept of environment is intuitively closed for here. To be closed, you have to be closed to something, and that something is the set of points which are not in the system. We call the environment. Okay? Is this close to the environment? Why not? Or let's take the example of a watch. Well, this is an electronic watch, sheet watch. It could be a mechanical watch. Just think of a mechanical clock, for example. Is it a closed system? Well, to be closed, the system should be able to function independently of its environment, right? Independently of its environment. It should be capable of seeking whatever goal it is seeking independently of its environment, meaning independently. By independently, we mean unaffected. So a clock, a mechanical clock, is the goal of a mechanical clock is to keep time. Is to tell us the exact time. That's the goal of the clock. Can the clock do this independently of its environment? Well, in many cases, it can do this reasonably well. But if the environment, for example, if it is very hot, if you take the clock to the North Pole, where it is very, very cold, maybe the clock will stop functioning. Or if it's a very hot day, and there is a lot of humidity in the atmosphere, etc., the clock may be affected from this and stop functioning properly. So a clock, under usual circumstances, can be assumed to be a closed system, but it is never a closed system altogether. You can never give an example of a closed system which exists in reality. There is no closed system. All systems are affected from their environment somehow. But if we can assume reasonably that the environment is not very relevant, or it's not very important, because nothing is taking place in the environment which will affect the system, then you can assume the system to be closed. This is what engineers do. Engineers work with systems that can be assumed closed. Can you give the only example of a closed system would be, I think, an abstract example. Like an algebra or mathematics. Mathematics is a closed system because it doesn't exist in reality. It exists in our minds, and it is a closed system. I cannot think of any other example which is a closed system. Such systems can be put into a laboratory and studied in isolation from the environment. Now, the concept of laboratory is quite important here. Engineers are capable of putting their systems in laboratories and study the system in isolation from the environment. What do they do in the laboratory, engineers? Well, the system can be analyzed by reducing it to its parts. Once you take the system on the workbench in a laboratory, you can take it apart. Just taking it apart is called analysis. You can analyze it by breaking it. Why do we do that? Why do we do that? Why don't we study the whole system, but reduce it into parts and analyze or study the parts? Well, obviously, because it is easier. For example, if I give you this laptop computer and I ask you to understand how it works, what is it made of, etc., by putting it in a laboratory, well, you have to take it apart. Okay? That's analysis. Understanding the parts is probably easier than to understand the whole system. Thus, analysis can provide knowledge and understanding of a closed system. Now, let's come to industrial engineers. All these work for non-IE engineers, let's say. But industrial engineers are concerned with purposeful systems that are open. That is, that cannot be assumed closed. Virtually all systems that you can identify in nature are open systems. They are in interaction with their environment. So you cannot assume the systems that, like a production system or an inventory system or a material procurement system, anything, or an educational system, whatever it is, or a traffic system, for example, cannot be assumed to be closed. Now, the difference between the systems that engineers work with and the systems with which we work, what's the difference? You see, these are working on goal-seeking systems. We are working with purposeful systems. So there is a difference between a goal-seeking and a purposeful system. A purposeful system is an organization with goal-seeking individuals. So that's the distinction. It's not like a mechanical clock, which is a single goal of keeping time, keeping correct time. The systems an industrial engineer is going to be concerned with is usually an organization full of individuals, or including individual human beings, each of which is a goal, it seeks a goal and a goal. Such systems are obviously much more complex than goal-seeking systems. Purposeful systems are more complex. But why can't a purposeful system be assumed closed? Well, we cannot assume a purposeful system to be a closed system because of the fact that they include individuals, and individuals have goals, aspirations, things that they would like to do, not only within the system, but also from outside, concerning the environment. We cannot assume a social system or a purposeful system to be a closed system. These goals that the individuals have can change from person to person. Normally, in an organization, you have members of the organization, we sometimes assume that they have the same objective because they are members of the same organization, like a political party. For example, the members of Adalet Partisi or GÜVEN Partisi can be assumed to have the same objective of coming to power, forming a government, etc. But they also have other goals than that. Concerning the party, they have other goals. So these goals will change from person, and also it will change from time to time, even for an individual. The characteristic of such systems is that they don't fit into laboratories. You cannot bring an open system into a laboratory, and therefore we cannot analyze it in a laboratory as normal engineers or research engineers are able to do. Understanding of an open system will not be possible through analysis only. Analysis of an open system is possible, although we cannot get it into a laboratory, obviously. For example, if I ask you to study an inventory system, you can still analyze it, break it into parts. For example, there's a warehouse. There's a method like the order point where you have to replenish the inventories. There's a system which records withdrawals from the inventory, etc. There are many parts in the inventory system, and you can analyze the inventory system by studying each part on its own. But you see, it will show us the structure of the system, the analysis. And it will probably explain how it works, how the inventory system works. And produces what we call knowledge. Okay? The end result of the thing that we get out of analysis is knowledge and not understanding. So now we are drawing a distinction between knowledge and understanding, and in the final slides of this lecture, I will have all these clear. What we mean by data, what we mean by information, what's knowledge, what's nonsense, etc. We'll come to that later. But here, at this point, we understand that analysis do not produce understanding. To understand an open system, we need to look at the larger system of which it is a part. This is the central idea of systems thinking. This concept is very, very important. In order to obtain understanding of a system, it is not sufficient to look at the parts of the system, but to look at what the bigger system is that contains this system. Okay? This is the central idea of systems thinking. And systems thinking includes and complements analysis in this way. We're not saying that analysis is useless. It is useful. It tells us how the system works. It provides us with knowledge. But this knowledge is not sufficient to obtain an understanding of the system. this is how ORIE differs from other engineering disciplines and from disciplinary science. Other engineering disciplines are not concerned with the concern of systems thinking. They of course have to know, for example, if an electrical engineer is working on a communication system. Of course, he has to know what this communication system is going to be used for. In what sort of larger system is it going to be embedded in? All of these questions are important for an electrical engineer also. But the electrical engineer has the luxury, has the opportunity to forget about, for the moment, about the larger systems and focus on the communication system itself. The industrial engineer does not have this luxury. You cannot work like this as an industrial. Always you have to keep in mind what the larger system